Good morning, good afternoon, and good evening, everyone. So today we're going to be going back to our calculus series, and we're going to continue doing double integrals using rectangles, right? And so we did do a couple of these back in our previous video. Let's actually do a brief review of what we basically did so far. So we did a brief review of what is a definite integral, and we said that it was a limit of Riemann sums, right? And we say that we can get the area under that curve if we take the integral of a plane curve, right? And then we move to talking about how we can use double integrals to get volumes. So not areas anymore, the 3D version, right? And so here we define a function f of two variables, right? And we say that we can get the area of this part here, the area of all of these stuff, all of that. So we can get the area of all of that stuff, right? And that's going to be, okay, more Riemann sums, a double integral, basically. And so it's also a double limit of Riemann sums, right? And then from there, what else did we talk about? Yes, so if the volume lies above the rectangle, then we know it's a volume, right? So similarly, if our curve in 2D, if our curve lies above the x-axis, then we know it's an area under that curve, right? And then we did some examples here of estimating the volume of solids. And so we did that using Riemann sum. And then we talked about the midpoint rule, but this time in 3D. So we use double integrals instead of a single integral. And so here we basically get the midpoints of x and y. And then we used a midpoint rule to calculate double Riemann sum. And then we got into this idea of iterated integrals where we solve an inner integral and then an outer integral. And this will give us basically the volume, which is a value, right? And so this is similar to partial derivatives, right? With Clairaut's theorem, we can integrate with respect to y first and then x, or vice versa, right? So Clairaut's theorem was stating that if we differentiate with respect to y, then x, it's actually equal to when we do it vice versa. And this is similar to integrating. We can also do it the same way. And this is Fubini's theorem, which is very similar, right? And then we did some exercises here where we used Riemann sum to calculate the sample points in the upper right corner. We did stuff like that. And then we also did a midpoint rule. And then we also did a double integral by first identifying the volume of our solid, right? And then we used Fubini's theorem here. So using Fubini's theorem, we converted it into an iterated integral. And then we get an answer of 3. And so here it's just the same process of doing iterated integrals again and again, right? Okay, now let's move to a different, let's do more examples here. Okay, so number 7, here we're being asked to calculate double integral, right? So how do we do that? Well, okay, here's what's given. This is our function of two variables, dA, and my bounded R is this value here. And my bounded, so that was my X, my Y is from there, right? So how do we do this? We can use Fubini's theorem, right? Let's quickly do that. And convert it into an iterated integral, right? Now, the question is this double integral continuous? It is, right? Or at least I think it is. How do we know it's continuous? Well, these are elementary functions, I would say. They're algebraic functions here at the numerator. This one's a quadratic function at the bottom. No, but again, it's rational. Anyway, we'll find out. We'll see. So we can say, okay, let's do dx dy. So let's integrate with respect to x first, and then with respect to y. Then we have our function. Right? It's the same thing as this. And then from there, we basically evaluate the integral. Now this is what we know as an iterated integral. Right? Let's go ahead and evaluate it. So here we have this thing. What is this? Here we treat x as a variable and y as some constant. Okay, this is... So, okay, this is going to be... Let's take out the variables, or the things that we don't need. Over x here. Oh, look at that. Now what is this? X over x squared plus 1, right? And then what do we do here? I'm thinking of using a u sub maybe. Let's try, why not? Let's do a u sub, let's see what happens. Let's take u to be x squared. And so my derivative is 2x dx. And so my dx is 1 over 2x du. And I think that works. Then when my x is 0, my u is 0. And then when my x is 1, my u is 1. So we have the same thing. So here we get 3y squared, 0 to 1. Here we have x over u plus 1, and then 1 over 2x du. And then we get to cancel this idea, right? So we can say this works. We have 3y squared. Oh, I get to put the 1/2 here, actually. So I do 3y squared divided by 2, 0, 1. This is 1 over u plus 1 du. And now I can integrate this nice and easy. Here I get 3y squared over 2. This one is natural log, right? Natural log of u plus 1, 0 to 1. And then we can plug in, so we get 3y squared over 2. This is ln of 2. Minus ln of 1, which is 0, right? So here we just get this number. And then from there, we integrate this thing now with respect to y. So here, this is 3y squared over 2 ln 2 dy. Then we can cancel all of the constants that we have. So this is 3 ln 2 over 2 y squared, right? Now we have a nice integral here. So this is going to be something. This is going to be what? Y cube over 3. And we should get, this is 2 cubed, that's 8 over 3. This is minus negative 8 over 3. So that's 16 over 3. And then we can cancel this 3 here. We can cancel this 2. So this becomes 8 ln 2. Then that's our answer, right? Nice and easy. So it is indeed that answer. Okay, let's do one more. And then we'll do more after. Yeah, I'm gonna end the video here after doing this because I actually have a class to attend to. Anyway, I'm just trying to review for my do bit by bit reviews for my exam on Thursday. Here again, we have the same thing. We want to calculate double integral. So really the cheat code to these math things is to memorize the steps. Oh, here, if we load this, our R is given in a weird way. That's the only difference. But it's actually just this. It's really just this. And this one is that. X in between 0 and 8 inclusive, as well as Y in between 0 and 1 inclusive. And so we can use Fubini's theorem again. I'm going to So Fubini's theorem states that if this thing is continuous, which to me it looks like it is, it's an elementary function, then we integrate by x then y or something like that. So this one's for y, this one's for x. So once we set up the iterated integral, we're good to go. Right? Okay, what do we notice? Let's evaluate this thing first with respect to x. What can we see? We can take out the 8, right? Let's take out the 8. So it's one of these step-by-step things that we have to do to make our lives easier. From here, I could do a u sub, right? Oh shoot, I don't think I can do a u sub. So it's either u sub integration by parts or something else. This is the same as x over 1 plus x. Let's say y is 1. How do I integrate that? Can't really do a u sub here. Can I do? What can I do? How do I reformat this thing? X over. There has to be a way. If this was. How do I format this? Uh, oh. Okay, it's one of these things where I just forgot how to integrate. If I'm being honest here. Yeah, let me just double check. How would you integrate such a function like this? I do a u sub of the whole thing. Let's try that actually. Let me do a u sub of the whole thing. with respect to x. Let's see how that would work. So if we do a u sub of this thing, my derivative would be what? Y. Then this would have been 1 over y du. And then when my x is 0, my u is just 1. When my x is 8, my u would be 1 plus 8y, right? And I keep going here. So 8, this is 1 plus 8y. Here I get x over u. And then this is 1 over y du. Okay. That that's weird. Now what happens? How come? Or did I mess something up? I think I messed something up. Because I'm supposed to have all U's. Or maybe I integrate it another way. It's also one thing, right? Yeah, let's try that, yeah? Let me integrate another way. This just could be a bit more complicated to do. Sometimes we just have to do it the other way around. Let's do dy here. And so we switch places. This becomes 8. This becomes 1 instead, right? So let's do that. 1, 1. Now this one's dy. Oh, look at that. Now this is 8x. This is 1, right? And then here I treat this as a u sub, because I could do that, right? This one's actually nicer. Du in this case would be the derivative of this thing. Y is my variable, x is my constant. So I would say this is x, right? And let me double check. Oh, wait a minute. Yeah, it's x. And so my dy in this case would be 1 over x du. Oh, so that is better. Yeah. And then when my y is 0, my u is 1. When my y is 1, well, then my u is 1 plus 8x. And so I actually get a new thing here. I get 8x, 1. My upper bound is 1 plus 8x. This is 1 over u, 1 over x du. And this gets canceled. Phew. And so I have this left. Like that. Now I can integrate. So I get this thing. ln of u. There we have it. So I would get 8 natural log 1 plus 8x, right? I don't include the 1 because that's just 0. Oh, that was a nice value. Wait, let me see. Oh, shoot. I think I messed something up. Uh-oh. Y is 1. Oh, so this is x. My bad. I knew it. I messed something up. This is x. This is x. So this is x. X. There we go. And then from there, I do it again. I integrate this thing with respect to x. 0 to 8. Now it's just a regular integral that oh, I have this thing. How do I integrate that? If I have a natural log, what do I do? I can't use up this one. I do an integration by parts. Usually, if I have an ln like this. So how's that gonna look like? Actually, is this an integration by parts? Or am I making it? I think oh, it is an integration by parts. So I need to find my uv minus v du. Right? That's the thing that I need to do. This is equal to my integral from u dv. Here, what's my u, what's my dv? That's the thing. My u is this whole thing. This could be my u. This is my dv. And so from there, I get u as this. My derivative would be, so the derivative of a natural log is 1 over 1 plus x dx. My dv was dx, and so my v is x. And so this is going to be what? uv ln 1 plus x. V is x, so I have x, minus the integral of v du. So v du. There we go. That's the thing that we have to go for. And then from there, I just evaluate. So here I would get, what in the world do I get here? I have to evaluate this integral here. And this one too. So this would be, what is this? I do it from 0 to 8. Right? 0 would give me nothing. So here I have 8 ln 9. Right? This one would give me 1 over... Oh, shoot. I think I went back to the... Uh-oh. Whoops. So I have to rewrite the whole thing. That's not fun. Wait a minute. What is this? Did I mess up again? I think I messed up again. Wait, did I get the right thing here? The integral from... Okay, so I did get the right thing. Now I just need to pick a v and a u. And I did. What was the u that was picked? Okay. dv... Oh, so dv is something different. So here they included 8. Okay, I'll include 8. Why not? Sure. So here I get this thing, right? ln 1 of 1 plus x, 8 dx for my dv. So this should look something like this. And so my v is just 8. Right? Now did I get it? Or no, my v is 8x because I'm integrating. U is that, du is that. Okay, so I basically get u v, so 8x ln 1 plus x from 0 to 8 minus my integral from here, which is u dv, 0 to 8. Oh, v du, my bad. So v 8x times this, so 8x 1 plus x dx. There we go. And now we can evaluate this. So the way we want to Okay. This gives me an answer of 64 ln 9. That's it. For the second part, this thing, I'll just write it like that. It wants me to rewrite it in a way like this. So this is 8 minus 8 over 1 plus x. And then that one's easier, right? So this is actually a partial fraction, I think. Or no, I don't think it is. It's just a way of doing it. And so if I do it that way, will I get, oh God, 8x minus, and then this was 8 ln 1 plus x. And then this is, what is that? 64 minus 8 ln 9. And then I want to combine those two. So I have 64 ln 9 minus 64 plus 8 ln 9, right? Because I combined those two. And it should give me 72, if I'm not mistaken. Yeah, 64 plus 8 is 72 ln 9 minus 64. Okay, so that's it for this video. I hope you guys enjoyed. Computation-wise, getting integrals is really, it's something else. But anyways, I hope you guys enjoyed, learned a lot. This is more on the computation heavy side, but anyways. Yeah, I hope you guys enjoyed, and I'll see you all in the next one.